Kids Hospital working with Dr. Yanis Taxidis. And he's going to talk to us about his work on rhythm production in the basal ganglia. Can you just put my collar? I can't see.
Is that coming through okay for everybody?
Rodrigo, are you in the room? Rodrigo? Next speaker? Yeah. Okay, just checking.
All right, good. Thank you. Can everybody hear me at the back? Am I okay? Yeah, perfect. So before I begin, I just want to say thank you to the organizing committee for giving me the opportunity to speak, and thank you to all of you for your attention. I'm excited to present this work. I think it's a good talk for the end of the day because the math is super easy. There's not going to be any eigenmodes or eigenvectors or eigen anything else. So I think we can all breathe, and hopefully it's a nice, relaxing, fun one. So classically, the basal ganglia has always kind of been described as gating action initiation, kind of controlling what actions happen. So the analogy you always kind of hear in undergraduate neuroscience classes is that it's like a system of brakes that are all constantly inhibiting the progression of any action. And then when an action should be performed, it kind of takes the brakes off of that specific, or the cortical regions encoding that specific action. However, more recently, there's been increasing amounts of discussion about the basal ganglia's role in not controlling when actions are performed or what actions are performed, but rather how they're performed. And you'll see this in monkeys. If you ablate the basal ganglia, they're still able to perform complex action sequences and initiate them at the correct times, but the speed or the timing with which they perform these trained actions is delayed or impaired. And moving into slightly more detail, it's been proposed by other groups, and we're going to kind of continue that proposition that the basal ganglia maintains a continuous and overlapping representation of movement parameters. So what I mean by that is within the basal ganglia, we're going to suggest that you don't have discrete populations of neurons that encode specific actions or specific action movement speeds or anything like that, but rather that the basal ganglia kind of maintains a continuous map of all possible or all like learned action sequences or action parameters. And as some like evidence, so maybe it's a little bit more clear, what I mean is within the striatum, which is the input region to the basal ganglia, you see neurons which don't show tuning only to a specific movement velocity, but rather they kind of have a tuning curve where they show the largest response to a specific velocity and then slightly weaker responses to movement velocities close to that kind of tune velocity. And then additionally, in mice performing more complex behavior, you kind of see this general trend of that more similar action or more similar behaviors have more similar representations within, or more similar, or are associated with more similar patterns of activity within the striatum. So kind of big picture question for this research is, based on the basal ganglia structure, which is relatively well characterized, if we assume that the basal ganglia is maintaining this continuous representation of how you perform an action, making that assumption, does this allow us to understand or explain features of movement in healthy and Parkinsonian patients? So that's obviously a massive question. So to kind of make it a little bit easier to study, what we're going to do is focus on a specific kind of case study of movement, looking at one specific movement and kind of hopefully, and hope that that generalizes to movement in general. So what we're going to look at is specifically finger tapping. And this might seem a little bit arbitrary. Why would we focus on this as opposed to any other kind of movement? And the major advantage you get with this is because finger tapping is such a finely tuned movement, you can kind of analyze like super fine trends in the variation within finger tapping, and it's not lost within kind of just the noise of performing that action. Where you can imagine with like a larger movement like walking, maybe some of the noise is kind of drowned out by just how large of a movement that is. And what we're going to assume the basal ganglia's role in controlling finger tapping is specifically, we're going to suggest that it encodes the tempo with which you perform a tap, because that's, or the tempo with which you tap, because that's the continuously maintained parameter within that movement. And it's analogous, you can think, to like walking speed or any other kind of like movement vigor that's been proposed elsewhere. Okay, so how are we going to do this? So what we've built is like kind of a simple firing rate model of the basal ganglia, where each region within the circuit is represented as a layer of 250 different units. So this kind of looks like a plate of spaghetti right now. So for all the simulations, the entire, like every region represented here is actually included. But for the sake of this presentation and understanding the results, we're going to focus on a much simpler version of the circuit. The basal ganglia, as you can kind of see, or I hope is somewhat clear, is that there's kind of these like segregated loops. So this is like a schematic of one loop through the basal ganglia, where you have a cortical population which sends relatively segregated projections to the striatum, which sends again relatively or very segregated projections to the GPI and the substantia nigra, which sends again segregated projections to the thalamus, and then the thalamus again sends segregated projections to the same like originally like the original cortical region. So you get like these segregated loops through the basal ganglia. And what we're going to suggest, as has been suggested elsewhere, is that each one of these loops encodes a different like pattern of action. And in this case, we're going to assume that each of these loops encodes a different or like a unique tempo. And then the tempo that the network like produces in its sum movement is going to be the like activity weighted average of the tempo encoded by all thalamic units, if that's clear at all. So just before I move on, I can kind of imagine is that when you get some kind of evidence that you should be tapping at some specific tempo, you'll get some kind of cortical representation that kind of provides evidence that that's a tempo you should be tapping with, and that sends a projection to the striatum, which is going to inhibit the GPI, which will then disinhibit the thalamic or the thalamus. And the idea is that like that disinhibition of the thalamus is what allows movement to actually occur. So what about those continuous representations that I was talking about earlier? So the way that we model those are by kind of breaking the segregation within these loops and allowing the cortex to send spreading excitation to the striatum. So I'll use an example. Let's assume that this cortical unit encodes tapping at 5 Hertz. It's going to send its strongest excitation to the striatal unit, encoding tapping at 5 Hertz, and then slightly weaker excitation to the striatal unit, tapping at 4 Hertz, and then 3 Hertz, and so on. And you can see the weight matrix, it just kind of follows a Gaussian for all of these units from here. And you can kind of, I hope you can see that that kind of replicates both those tuning curves that you see within striatal units where they have kind of like a preferred firing rate or preferred tempo in this case, or preferred movement parameter, and then they show kind of like weaker firing for similar patterns of movement. And then also, I hope you can see that this will kind of yield, well, so if you can imagine, let's say when this cortical unit becomes active, what you're going to get is a bump of activity on the striatum associated with that cortical activity. And then let's say cortical unit encoding or cortical population representing a slightly similar action becomes active, you'll get an overlapping but slightly shifted bump of activity on the striatum. So you get like both those tuning curves within the striatal units, and then also these overlapping kind of bumps of representation on the striatum associated with similar actions. And then additionally, what we're going to suggest is that dopamine encourages like recurrent excitation through these loops by modulating activity in the striatum, specifically within this pathway. So it's highly simplified, but all we're going to assume is that with higher levels of dopamine, you get higher levels of excitation within the striatum. Okay, so we can move on to some results. So within all these figures, which I'm going to show a couple of, each one of these blocks represents a different unit within the network, and then each row is a unit, and then it's showing its activity over time. So what we can see is that if we give some kind of external input to kind of cue the network to begin firing at a specific tempo, we get this kind of maintained spreading bump of activity that can continue even in the absence of initial input. So that's kind of intuitive because you can imagine once you begin tapping, you don't need to consistently like think about that you don't have to consciously maintain that tapping sequence. You can kind of exist on its own without any kind of like conscious or outside of conscious control. And then, as I kind of mentioned, we're going to assume that the network taps, or that the encoded tempo, the tempo encoded by the network is, as I mentioned, the activity weighted average of all the thalamic activity, but you can kind of just imagine it as the center of the bump. So wherever the center of the bump is in the thalamus, the associated tempo is going to be the tempo that the network produces. So you can see here, just due to random noise, the encoded tempo kind of wobbles around a little bit, which will become relevant soon. Okay. So, and then as I kind of mentioned, we're going to be really interested in the effects of dopamine on this network. So like I said, dopamine kind of encourages this recurrent excitatory activity through the network. And as you reduce it, the amount of recurrent excitation decreases to the point where the bump no longer is maintained. And it's a little bit hard to see, but as the dopamine decreases, you see slightly more drift in the location of that bump in the thalamus. So if we take the center of that bump to represent encoded tempo, and you plot that as a trace, you can see there's drift even in both networks, but as you decrease the dopamine, you get an increased drift in the tempo encoded by the network. So not unexpectedly, if you then kind of simulate taps by the network at the tempo encoded, you would expect, and you do see, a higher intertap interval variance. But this isn't really groundbreaking because all we've done is we've said, okay, we have a network that encodes tempo and we let it drift and then we see a drift in encoded tempo. So why is this interesting at all? The reason we kind of care about this is because if you look at Parkinson's patients where you say, okay, just maintain some kind of, just tap at whatever frequency feels best to you and you just let them continue that tapping, what you see is they also have a significant increase in the variance of their intertap intervals. Okay, but I can hear what you guys are saying. How do we know that this is coming from the basal ganglia or coming from tempo, or how are you associating these two results at all? And what we can do that's kind of interesting is you can break down the variance between two taps into 3 different sources. The first of which is clock variance, which is intuitively just you have the correct beat and you know how quickly you're supposed to be tapping, but you're just failing to track the phase of the beat as it progresses, or that you're failing to track which phase of the beat you're at across time. There's motor variance, which is when you know the beat that you're supposed to be tapping on and you know where you are in the beat, but there's noise in the actual execution of the movement. And then lastly, there's drift variance, which is you know where you are in the beat, but you're just off beat, you're tapping at a different tempo. And we can kind of break down the variance in our intertap intervals into these 3 sources by looking at the covariance across intertap or consecutive intertap intervals. And I can get into more detail if anybody has any questions. But what we see is that if we break the variance from the tapping from our network and the tapping from Parkinson's patients, we see that there's only a significant increase in both data sets within the drift variance. So kind of not unexpected, we only see a significant increase in the drift variance in our network, and we only see a significant increase in the drift variance in the Parkinson's patients. So intuitively, what that means is that these patients aren't struggling with tracking where they are in the beat, what phase of the beat they're at, and they're not actually struggling kind of unexpectedly with producing the tap itself. They just seem to be drifting more in the tempo that they tap at. And what we're going to suggest kind of like as a big picture here is the reason that these Parkinson's patients have this increased variance is due to the reduced dopamine causing a weaker recurrent excitation through that network so that it's less stable. They have less stable representations of how they should perform the action in their basal ganglia due to that weaker recurrent excitation. Sure. So I'll go kind of quickly through the secondary result. And another kind of thing we see with Parkinson's patients is that they can struggle to, or they can have these kind of like spontaneous bouts of freezing. Well, they'll be walking and then suddenly stop and they can't begin motion again. What we see within our network is if we reduce dopamine, at some points, if the dopamine reaches some kind of critical point, the network kind of fails to maintain a continuous representation of action. The recurrent excitation is no longer strong enough to maintain that bump. And what we suggest is this is kind of analogous to freezing because if you can't maintain a representation of how you should perform an action, we're going to suggest that you can't perform the action at all. But what we see is that if you give Parkinson's patients a beat to tap or to walk along to, they're able to walk both with reduced freezing, but also much more smoothly. And what we suggest is that this beat kind of acts as an external cue to how to perform the action. They know now with which tempo they should be walking. So we can kind of model this like the reception of this beat as this external excitation landing on the same tempo that the patient is trying to walk on here. So we have this external input kind of reinforcing the internal recurrent excitation. And we see that causes a decrease, or can in some cases prevent freezing. So I'll skip this for now. And then lastly, does this model make any predictions that can be tested elsewhere? And what we see, or what we suggest, is that due to this kind of like weaker recurrent excitation that we expect to see in Parkinson's patients, we expect that they should be more suggestible to external cues. So if you give the network kind of like a shifting pattern of input, you can see that the patients or the networks with lower dopamine show a larger shift in the encoded tempo, and which we would suggest would correspond to larger shifts in the taps that they produce. So kind of big picture, we kind of expect that due to weaker internal representations of action, Parkinson's patients would be more susceptible to external cues. So just some conclusions. We designed a novel kind of model of the basal ganglia where it's not solely involved with controlling what action is performed or when it's performed, but rather how it's performed. And we suggest that the recurrent excitation within that circuit, as well as kind of these spreading activations or these like spreading patterns of excitation, allow it to be that representation to be maintained without external input. And then we suggest that dopamine isn't only involved with initiating action, but also kind of stabilizing its representation over time. And some of the patterns of behavior we see in Parkinson's can be understood as a failure of that system. So I just want to say thank you to a couple of people. Of course, Dr. Jonathan Cannon for massive amounts of support and guidance through this project, and then as well as Dr. Don Rose for the Parkinson's data set that we analyzed, and then all the other members of the Meter Lab and the McMaster Department of Psychology, Neuroscience, and Behavior for helpful discussion. And if anyone's interested, this manuscript is available online. So thank you.